All right, ladies and gentlemen, this is going to be review video 14, all about phase changes. So let's start by talking about what even is a phase. Well, it's a state at which matter can exist. So that's a pretty easy definition. There are three main phases that we're going to talk about, which you have no doubt already heard about. We have the solid phase here, the liquid phase here, and the gaseous phase there. Their abbreviations are exactly what you might expect, S, L, and G. But I do want to point out that we use a cursive L for the liquid phase, because if I just use a lowercase regular L, it looks like the number 1, and that can be kind of confusing when we're embedding that information into chemical formulas. On the side here in yellow, there's two other phases, one of which we will deal with a lot and one of which we will almost never deal with. So plasma is another state of matter that can exist when we've added enough energy into a molecular sample for the electrons to be ripped away from the nuclei entirely. But we are never going to do an experiment specifically with or about plasma because we do not have the ability to isolate plasma safely in a high school lab. And also it's kind of beyond the scope of this class anyway. But aqueous over here, abbreviated AQ, we will deal with this one a ton. And aqueous specifically means to be dissolved in water. So when we start dissolving a bunch of things in water and doing equilibrium chemistry, you're going to see a lot of aqueous things. All right, so let's talk about the parameters of solid and liquid and gas. Anything that is in a solid state has what we call a regular arrangement. Right? And you can see that in this picture over on the right. All of my particles are arranged in neat little rows. They're right next to each other. They look very, very regular in their arrangement. One of the earmarks about solid, other than that regular arrangement, is that those particles are very close to one another. And you can kind of see over here in red these little lines surrounding one of the particles. And that means that there's a little tiny bit of movement. And that tiny bit of movement is just them vibrating in place very slowly. And that represents a low amount of kinetic energy, because kinetic energy is all about the energy of movement. So solids do not have a lot of that because, again, they're stuck in place pretty much all of the time. But as such, as they are stuck in one regular arrangement, they do have a very high density. Liquids, on the other hand, are a little bit different than solids. So we can see in this picture over here, those molecules or those particles do not look like they have a regular arrangement anymore because they don't. They have what we call a variable arrangement. And you can kind of think of that as the ability to take the shape of whatever container they're in. Because if you have a sample of liquid water, you could pour it into a cup or a mug or a bottle, a beaker, an Erlenmeyer, and it's going to take the shape of whatever container it occupies. The particles themselves, though, despite the fact that they can move and slide around one another to create this variable arrangement, are still going to be pretty close together. However, you're noticing there's a little bit of separation between some of them while others of them are right next to one another. That variability comes from those particles' ability to move around. And because they can move around and they're not locked in a regular arrangement, we say they have a medium or a mid-range amount of kinetic energy. And because there's a little bit of separation between those particles, we say that there's a medium or mid-range density. Gases, on the other hand, also have a highly variable arrangement because, again, gases, you can even see it over here in this picture, those molecules are all over the place, right? Those particles are also very far apart from one another. There is a ton of separation between all of these particles. They are cruising around. They have a very high amount of kinetic energy, which means they're moving very, very quickly around their container, and they're going to bounce off the walls of their container, creating gaseous pressure. Because they are so far apart from one another, we also say that they have a very low molecular density. Now, there's one exception to that density rule, that solids are high density, liquids are medium density, gases are low density rule, and that is water. specifically. Water is actually more dense in the liquid state than it is in the solid state, which is the reason that ice is able to float on top of water. And the reason that that happens has to do with something called intermolecular forces, or IMFs for short. So over here in the left picture, this left-hand picture represents the solid state of water. You're seeing a bunch of dotted lines in between the water molecules, right? Dotted lines are how we represent intermolecular forces. And intermolecular forces are attraction between different molecules. So in this case, this water molecule is attracted to this water molecule and this one and this one and this one a little bit. However, it's not as if they're actually bonded chemically. There's a little bit of attraction there, and that's what these dotted lines in between are representing. Specifically, the intermolecular force that water is able to do is called hydrogen bonding, which is a little bit of a misnomer because it's, again, not an actual bond, but somebody just named it hydrogen bonding, and so that's what we call it. Because water molecules can hydrogen bond with a bunch of other water molecules, it kind of forces the solid structure into like a faux crystal lattice, kind of like an ionic compound, except it's not an ionic compound. And because that happens, there's actually more distance in between water molecules in the solid state than there is in the liquid state. And you can see that represented in this picture. So that's why water is an exception to that. In terms of why we care that water is an exception to that, it's because it's really important for things like the evolution of life. Because if you consider like a frozen lake, right? Lakes don't tend to freeze all the way through. There's a sheet of ice on the top that might penetrate down into the lake a little bit, but the bottom is going to remain liquid while the ice is going to float on top, which means that life forms on the bottom can still survive even when it gets really cold outside. So that's important for species survival and evolution and things like that. So that's why we care about it. All right, so we've talked about the different phases. Now let's talk about phases and how they change, right? Because one sample, as we know, let's say water, can be in solid state or liquid state or gaseous state or whatever. And to change phase, those molecules of water are either going to absorb or release energy to change phase. So, looking at this diagram, we can see that as we travel up the diagram, we are gaining energy. So let's say that my water is ice, actually, in solid state. If I want to melt that ice, it means that the water molecules need to absorb some energy to move into liquid state, and so that would be melting. If my water is in liquid state over here and I want to turn it into a gas, we got to absorb more energy to do that, to vaporize or boil. And finally, if we wanted to turn that gaseous water into a plasma, we would have to have those water molecules absorb a ton of energy until their electrons got ripped away and it might eventually become a plasma. Every single phase change that you see in this diagram that's highlighted in red is what we call an endothermic phase change. And endothermic phase changes just mean that those molecules have to absorb energy to change phase, because we know as we move from solid to liquid to gas, we are moving faster. So they have to absorb that energy to move faster. However, if we wanted to do the opposite, let's say we wanted to take that cool plasma water and turn it back into a gas and back into a liquid and back into a solid, those molecules would have to release the energy that they have to do that. And so that's why all of the blue ones are going to be exothermic phase changes, because exothermic means to release energy. And to change phase that way, molecules are going to release energy to do that. I want to make this clear though, phase changes, exothermic and endothermic phase changes are not the same thing as an endothermic or an exothermic reaction, because phase changes are reversible, right? Water can be ice, turn into water, and then refreeze. However, chemical reactions tend not to be as easily reversible as that. And so those are two different things. So I don't want you to think that endo and exo phase changes and endo and exo reactions are exactly the same, because they're not. All right? Other things to note. about phase changes. When molecules change phase, they are either breaking apart from one another or they are coming back together. But what I want you to understand is what's breaking and reforming are intermolecular forces, forces between different molecules. So I'm going to write that down, between different molecules. That is what's breaking and reforming when molecules change phase, not chemical bonds. So we're not breaking the covalent bonds of water. This bond here does not break. That remains solid and intact when water molecules change phase. It would be the intermolecular forces between another water molecule or two adjacent water molecules. This is what's going to break and reform if that water changes phase, right? The only exception to that rule that I just gave you is an ionic compound. All right, so let's take a look at an example of that. So we have up top here, we have water, which is our covalent substance. And then down here, we have just a general salt or a general ionic substance. All right, so if I'm going to melt water, and again, over here is our solid representation of water. What I am doing is I am breaking these intermolecular forces between the water molecules, but the water molecules themselves do in fact stay intact, right? But if I melt an ionic substance, that process is a little bit different because what's breaking is the attraction between the oppositely charged ions. And you can see that over here because the ions have moved away from one another. So specifically, what I am doing is I'm breaking the ionic bond when I melt an ionic substance. And it's probably pretty logical to assume that IMFs, what's breaking up here in my covalent substance, since they're between different molecules, those are a lot weaker and a lot easier to break than a true chemical bond, a true ionic bond. And so when you think about the trend that we saw in the lab a couple of weeks ago, that your covalent substances tended to melt first and your ionic substances didn't, this is why. Because breaking a true chemical bond, like an ionic bond, requires a lot of energy. And that's why your ionics are going to tend to have such high melting points and such high boiling points, because it takes a lot of energy to do that, versus breaking your weak little intermolecular forces between different molecules. So if you're struggling to understand any of that, please ask me questions in class.